Welcome to Pi Calculations, an interactive exploration of the most famous number in mathematics. This app demonstrates 9 different ways to approximate pi, from probability-based experiments to powerful algorithms. For a deeper dive, tap the info icon on any panel to learn how each calculation works. Discover how dropping needles, generating random points, or summing infinite series can all lead to the same mysterious constant. Watch these diverse methods race to calculate pi in real time, and press start to see which gets closest, fastest. First, we have Buffon's needle, a classic problem in geometric probability. Imagine dropping needles onto a floor made of parallel wooden planks. Some needles will cross the lines between planks, while others won't. This experiment reveals a surprising connection. Pi can be estimated by multiplying twice the number of needles dropped by the length of the needle, and then dividing by the number of needles that cross a line, and the width of the plank. The more needles you drop, the more accurate your estimation of pi becomes. The circle points method, also known as Monte Carlo circle, is another probabilistic approach. We inscribe a circle perfectly inside a square and then scatter random points throughout the square. By counting how many points land inside the circle versus the total number of points, we can estimate pi. The ratio of points inside the circle to the total points is approximately the ratio of the circle's area to the square's area. Multiplying this ratio by 4 gives us an increasingly accurate value for pi as more points are added. Monte Carlo integration uses a similar random sampling concept to find the area under a curve. To calculate pi, we evaluate the area of a quarter circle with a radius of 1. By generating random points within a 1x1 square that contains this quarter circle, we can determine the ratio of points that fall under the curve. This ratio approximates the area of the quarter circle, which is pi divided by 4. Multiplying this result by 4 provides another clever, probability-based path to estimating pi's value. The GCD method offers a unique way to find pi by looking at the probability that two random numbers are co-prime, meaning their greatest common divisor is 1. It turns out this probability is 6 divided by pi squared. By generating many pairs of random integers and calculating the fraction of them that are co-prime, we can work backward to solve for pi. This method elegantly links number theory with the geometry of the circle, revealing pi in an unexpected place. The Leibniz formula is one of the most elegant and famous series for calculating pi. It is an infinite alternating series that starts with 4 and then subtracts 4 divided by 3, adds 4 divided by 5, subtracts 4 divided by 7, and so on, continuing with the odd numbers. While beautiful in its simplicity, the Leibniz series converges very slowly. This means it requires a huge number of terms to produce even a few accurate decimal places of pi, but it serves as a wonderful example of an infinite series. Machin's formula, developed in 1706, was a major breakthrough for calculating pi manually. It represents pi as a combination of two arctangent functions with much smaller arguments, specifically 4 times the arctan of 1/5 minus the arctan of 1 over 239. This formula converges much faster than simpler series like Leibniz's. Because of its efficiency, Machin's formula and its variations were the primary methods used to compute pi to hundreds of decimal places for centuries, long before the age of computers. The Bailey-Borwein-Plouffe, or BBP algorithm, was a revolutionary discovery in 1995. Unlike most formulas that must calculate all preceding digits to find a specific one, the BBP algorithm can compute any individual hexadecimal digit of pi without calculating the ones before it. This digit extraction property makes it incredibly powerful for verifying computations and for parallel processing. It provides a direct, surgical strike to find a specific part of pi's infinite sequence, a feat previously thought to be impossible. The Nilkantha series is another infinite series for pi that converges much more quickly than the Leibniz formula. It starts with 3 and then adds, subtracts, and adds a series of fractions. The pattern involves fractions with denominators based on products of 3 consecutive integers, like 4 divided by 2 times 3 times 4, then minus 4 divided by 4 times 5 times 6. Its faster convergence means it yields more accurate results with fewer terms, making it a more effective, yet still conceptually simple, method. The Ramanujan series, discovered by the brilliant Indian mathematician Srinivasa Ramanujan, are a family of formulas for pi that are astonishingly powerful. These series converge extraordinarily fast, adding multiple correct digits with each new term. They are much more complex than series like Leibniz or Nilkantha, involving factorials and large constants. Their incredible speed made them instrumental in modern, high-precision computer calculations of pi, pushing the known digits into the trillions. In summary, this app provides a fascinating visual race, showcasing the diverse ways mathematicians have approached the calculation of pi. From the random beauty of probabilistic methods to the precision of infinite series and advanced algorithms, you are seeing a live demonstration of mathematical history and innovation. Each method, with its unique strengths and weaknesses, offers a different perspective on this fundamental constant. We hope you enjoy this journey through the many paths to pi.